Either you believe man-made climate change is a nightmarish existential threat to civilization, or you lack basic critical thinking skills and you're about to write something dim in the comments. Whichever it is, let's at least agree mankind is dumping too much carbon into the atmosphere. Not convinced? Here's some numbers. Prior to the Industrial Revolution, Earth's atmospheric carbon dioxide concentration was chilling somewhere around 280 parts per million. If we want to keep our planet habitable, respectable climatologists all agree we need to keep that number below 350 parts per million. Tops. Anyway, since you ask, as of this year, we're roaring past 420. Nice, except not. Of course, we all know emitting less carbon dioxide would help avoid a catastrophic runaway greenhouse effect that will in turn destabilize ecosystems, interrupt food supplies, and prompt a historic global refugee crisis. But what if there was a way of extracting the carbon that's already up there, in effect setting back the clock? Join us today as we anxiously gaze at the skies and ask, can carbon capture save the planet? Carbon capture is a very new field, and it's evolving rapidly. But for our purposes, let's say that there are essentially two types of carbon capture and two types of carbon disposal. Carbon dioxide, CO2, can be removed from industrial emissions at source, say the belching chimney of a coal-fired power station, before it's released into the atmosphere. This so-called flue gas approach is already in use at certain select facilities, like the Boundary Dam coal-fired plant near the town of Estevan in Saskatchewan, Canada. This specific process, which employs sophisticated ammonia-based chemistry, successfully captures around 1 million metric tons of CO2 every year, or 90% of the Saskatchewan plant's emissions. The downside is the equipment to make that happen cost $1.3 billion. The other kind of carbon capture is far more exciting and is named DAC, or direct air capture. DAC employs giant banks of fans pretty much, which suck already emitted carbon out of the ambient atmosphere. This technology is very promising, but has yet to be deployed at any useful scale. More on those shortly, after we touch on the vexed question of what actually needs to be done with that carbon once it's captured, either through flue gas extraction or snatched out of thin air. Again, there are two broad approaches here. CCS stands for carbon capture and storage. Under CCS, the recovered CO2 is stashed out of harm's way, typically underground in secure rock formations. CCU, on the other hand, stands for carbon capture and utilization. With CCU, the carbon is actually recycled and put to good use, for instance as a raw material or feedstock. This sounds great, but raises plenty of questions of its own. Let's look at a couple of CCS, carbon capture and storage, initiatives happening right now. Northern Lights is a hyper-ambitious project being carried out in collaboration between oil giants Shell, Total, Equinor, and the Norwegian government. The idea is that emissions will be extracted from industrial flue gases from factories across Norway, eventually all across Europe, and carried over pipelines to a coastal terminal at Øygarden on the North Sea coast. From there, specially designed ships will ferry the noxious CO2 waste out to sea, where it will be injected into storage reservoirs 2,600 meters beneath the seabed. The first project of its kind to be attempted at scale, Northern Lights promises it can initially store up to 1.5 million tons of CO2 a year, which should increase to 5 million tons a year as the model, CCS as a service in effect, proves its efficacy. We'll see anyway when it's up and running in 2024. If you can't wait that long, another very exciting carbon capture and storage scheme named Orca comes on stream this September in Iceland. Conceived by Swiss startup Climeworks, Orca catches its carbon via futuristic direct air capture, essentially running gigantic banks of fans which suck CO2 into clever filters, which are then heated to separate the pollutant before pumping it into safe basaltic rocks far below the rugged Icelandic landscape. The question of where we shovel that CO2 is of course central to the problem of carbon capture. Basalt rocks are ideal, not only because they're very common, but because CO2 reacts with basalt's naturally abundant magnesium and calcium, transforming the unhelpful element into solid minerals like dolomite, calcite, and magnesite. If the end result is rock solid, the theory goes, it's also going to be stable and won't trouble the atmosphere and by extension, society anytime soon. Oil and gas reservoirs of the type Northern Lights wants to use to stash CO2 under the North Sea are similarly helpful. They're obviously porous and can store a lot. We know this because that's where much of the oil and gas we've been merrily torching for over a century first sprang from. There's no shortage of underground space. In fact, research suggests the United States alone has enough subsurface capacity to store some 10.8 trillion tons of the stuff. Anxieties naturally crop up around contamination of subterranean watercourses, but in most cases, the deep saline groundwater systems at threat aren't part of the drinking water system anyway. For a long time, incidentally, scientists contemplated dumping CO2 into the deep ocean. At sufficient depth, carbon dioxide is denser than water, so it should stay in place indefinitely. However, there's no telling what that might do to fragile marine ecosystems, and the somewhat unpredictable nature of powerful ocean currents make it all just a bit sketchy. Far more exciting is the prospect of CCU. Remember, that's carbon capture and utilization. Lots of very clever people and startups are figuring out ways of using carbon destined to float around in the atmosphere as handy terrestrial products. Take these snazzy H&M sunglasses, crafted from CCU-based carbon-negative thermoplastics, or these carpet tiles by American firm Interface. Climeworks, them again, have figured out a way of repurposing captured atmospheric carbon as the gas that makes your drinks fizzy. Australian company Mineral Carbonation International wants to utilize carbon in bricks, which would handily store a whole bunch of carbon securely for at least a century, part of the firm's ambitious initiative to lock 1 billion tons of CO2 into its products by the year 2040. The great sad irony of carbon capture and utilization is that, for now at least, its main commercial use is the mucky business of EOR, or enhanced oil recovery. Under EOR, CO2 is pumped underground at drilling sites in order to help drive precious crude oil reserves to the surface where they can be more easily extracted. If you're feeling squeamish about the sound of that, fair enough. Somewhere around 3/4 of all subterranean carbon sequestration happens in the name of EOR. It's good in that carbon that would otherwise wind up in the atmosphere is stashed out of harm's way, but obviously bad in that it ultimately leads to the burning of still more fossil fuels, and we really do need to start moving past that. Still, encouragingly perhaps, a prominent EOR facility in Petronova, Texas recently closed after the pandemic-related oil price crash made EOR no longer financially viable. In either case, it doesn't actually matter from an enhanced oil recovery standpoint whether the carbon used for pumping out oil comes from recovered emissions or virgin mined carbon, which is of course cheaper and sneakily preferred by the oil giants. This brings us to the fundamental problem of scaling up carbon capture schemes. For now, there's no great financial incentive for any bright young startups to develop and scale their technology. Electric cars, and to a lesser extent solar panels, are a shiny futuristic technology that people are happy to splash out on. Elon Musk can grow as rich as he likes selling fast cars, but carbon capture is a lot more humdrum, with the benefits only likely to be felt many years or decades from now. It's hard to market and hard to get excited about. It needn't be this way though. Carbon obviously has value. It's useful. Policymakers just need to find a way of making captured carbon more cost-effective than virgin carbon. In order to meet the International Panel on Climate Change's target, removing 10 gigatons of CO2 net from the atmosphere by middle of this century, a vast industry needs to be built, and it needs to be built now. The Northern Lights project off the coast of Norway is a promising start. Climeworks reckons about 80 million of its extraction units, which can be placed more or less anywhere on Earth, ideally near renewable sources of power, could make a significant dent in atmospheric carbon. That sounds like a lot, but it's roughly the number of cars that are already manufactured every year. Where there's a will, there's a way. In truth, carbon capture and utilization will only ever be a sideshow. Much of the recycled carbon, used for instance in food or alternative fuels, will just end up back in the atmosphere at some point anyway. Current technologies on the drawing board to, for instance, apply molten electrolysis to make recovered carbon into nanotubes that replace construction steel would be great, but are too speculative to rely on at this early stage. So for now, smart subterranean sequestration is the path forward. And with dizzying incentives on offer to whichever genius figures out how to do that at a useful scale, not least our mate Elon's generous $100 million Carbon X prize fund, hopefully the grubby profit motive will save our collective bacon after all. Because as a civilization, we really can't afford for carbon capture to remain an underground technology. What do you think? Is there a better way of reducing atmospheric carbon and averting runaway climate change? Let us know in the comments, and don't forget to subscribe for more thoroughly captivating tech content.